Welcome to the Toon Show. I'm your host, MC Toon. I love to have fun promoting science and critical thinking. Often I do this by debating against flat earthers, anti-5G nutters, and other science deniers on my YouTube channel, MC Toon Live. I also feature pre-recorded videos explaining science in an irreverent way on my Conspiracy Toons channel. Jump on YouTube to see them and subscribe while you're there. You can search YouTube for them, or they are linked on my website at mctoon.net. On this podcast, I feature some of the live debates I've done, as well as podcast exclusive interviews with sciencey smarty pants guys. And today, the sciencey smarty pants guy is Eric, who is a grad student studying astronomy. But before that, I want to introduce Industrial Nerd, who's my co-host today, who was the smarty pants guy introduced previously. Welcome, Industrial Nerd, as the co-host.
Thank you, Toon. Thank you.
All right. That's it. That's all you get.
That's fine.
If you're interested more, Industrial Nerd was in my previous one, actually episode 0 of season 1. But now here to the man of the hour, Eric. Eric is studying astronomy, and I'll let you explain where you're at and what you're doing with astronomy.
All right.
Go ahead, Eric.
All right. Well, currently I'm a master's student. My master's is technically in physics, but my research is in observational astronomy. I have a bachelor's degree in both astronomy and physics, and then starting in August, I'll be starting a PhD.
Excellent. And how long will the PhD program take? Will it be the normal 12 years?
It'll be 4 to 6 years, probably.
Oh my goodness, that's still a lot. I was kidding about 12, and you went half of that, which is still, that's a lot.
Yeah.
So, all right. So you said your bachelor's was
double in astronomy and physics.
Okay, and your master's will be physics.
Physics.
Technically, but you're all right. And what's the PhD going to be?
The PhD is technically going to be physics as well, but It'll be, again, research in astronomy.
It's heavy in physics in astronomy anyway.
Yeah. So, I mean, astronomy is physics applied to space. So
yeah. Excellent. All right. Well,
so would that be astrophysics, astronomy and physics, or because I don't follow the field very well? So
they're actually kind of separate-ish, because I mean, astrophysics is more kind of the theoretical side of it, and then for me, I'm doing observational.
Okay, makes sense.
Awesome. Well, you have you had something prepared. You're going to explain to us and let us know some interesting stuff. So go ahead.
All right. So what I'm doing today is on how we measure the distance to stars, and I had to get out my old astrophysics textbook, and it is nicknamed the Big Orange Book. So thanks, Bob.
Thanks, Bob.
Thanks, Bob.
So there's a bunch of different ways for measuring the distance to stars, and the one most people know about is stellar parallax, which is for the closest stars. And that it actually takes a full 6 months to do that, because you need the full diameter of Earth's orbit. And then for that, what you have to do is you look at the star at one point and compare it to the stars in the background, and look at it again 6 months later and compare it to those same stars in the background and see how much it's moved. And from that, you can get what's called a parallax angle. And from that angle, there's a small angle approximation where the tangent of x is about equal to x in radians, if it's an extremely small angle. And then from that, you have to convert the radians to arc seconds, because it's a really small angle. It's usually like 1 arc second is actually a pretty large parallax. And then you do, for the distance, you do 1 AU, which is 1 astronomical unit, which is the distance from the Earth to the sun. You do 1 over the parallax angle, which gives you the distance in parsecs. 1 parsec is about equal to 3.26 light years. And then another way you can do it, because the parallax angle only works to about 600 parsecs. So after that, you have to go to a thing for apparent magnitude and absolute magnitude.
So can I ask how many, do you know off the top of your head about how many stars are within the range where we can measure using parallax?
I'm not sure. It's in the thousands, but it's a lot of stars are really dim that we can't see.
Okay. With our eyes, we have to use.
Yeah, we have to use telescopes.
Yeah.
So either really big ones or and especially if you're in a light polluted area, you definitely won't be seeing that many.
Yeah, that's why they like mountaintops and stuff.
Yes. So the second way you have to do it is with magnitudes, which is the apparent magnitude is what we see in the sky right now. And then there's something called absolute magnitude, which is how bright an object would be if it's 10 parsecs away. It's 10 parsecs is used because the magnitude scale is logarithmic. So since it's a log 10 scale, just put it at 10.
Okay.
Makes it a lot easier. So,
and that's because it's an inverse square relationship.
Yeah, that's for the flux and the luminosity. Yeah.
Okay, we're not there yet. I'm getting ahead.
Not quite there. And actually, for the people that are seeing it on YouTube, I can actually share my screen. I have some math equations.
I like math. I do enjoy it. Up to a certain point. Good. Once you get to a certain point, I think everybody hits a point where like, oh, that's too many squiggles.
Yeah. This is the point where it's
what does that symbol mean?
Because this is actually funny because this is where it's just simple algebra. But this is where in astronomy 101, people's mouths are up and are like, I didn't know there was math in astronomy.
Oh my gosh, yes.
Which is so funny to me because it's like when I took the class, I actually heard someone say that.
All right, you should be able to share your screen.
All right. Sure. All right, here we go. So these are the first couple equations that you'll see. So the whole thing for the magnitude scale is that a difference in 5 magnitudes is actually 100 times difference in the brightness. So here's a little ratio you'll see, which is F2 over F1 is equal to 100 to the M1 minus M2 divided by 5. So
what are these? What's F1 and 2 and what's M1 and 2?
F1 and F2 are the flux, and then M1 and M2 are the apparent magnitudes of 2 different stars. This is for where you have to compare 2 different stars.
Okay.
So the easiest comparison is using the sun. And then also another way of writing that same equation is with it in the log scale that's on the right side of this. M1 minus M2 is equal to negative 2.5 log 10 of F1 over F2.
All right. So so you just solve for M1 minus M2.
Mm-hmm. And then, so that's the ratio for the apparent magnitudes. And then for getting the absolute magnitudes, which will end up with getting you the distance, the luminosity is what's really important. And I have here, you'll see a very crazy graph, which I'll explain in a second. But
that's all right. So let me just for a second, if you're listening to this podcast instead of watching it, you can see what he's sharing on YouTube if you just search for Toon Show on YouTube.
Yeah, it's there's a lot of graphs and just some math, so it's a little hard to explain just talking it out unless you actually know some of the math yourself.
Yeah.
But the really important thing in astronomy is the luminosity, and the luminosity requires that you have the radius of the star and what's called the effective temperature. So the temperature of like the surface of the star. So like the surface of the sun is about 5,800 Kelvin. So temperature you have to use Kelvin for.
Yep.
The way that you get the temperature is actually you have to use 2 separate filters for, oh my God, my cat. You have to use 2 separate filters for it. And the most common that's used is there's a B filter and a V filter, which is blue and visual. So.
And this is a physical filter you put in front of the telescope?
Yes.
Okay.
different telescopes have different filters. Like the Hubble telescope has a lot of different filters, which I'm using different filters from Hubble data for my research. But so you also need to get the radius of the star, which is a little more difficult because you have to know if it's a giant star or if it's like a regular star, which is called if it's on the main sequence. So stars like the sun are on the main sequence, but stars, if you like Betelgeuse, is a red supergiant. And the way that you can actually tell if it's a giant or not is through spectroscopy of the star. So every star is going to have its own spectral lines, and they're all kind of categorized. But the way to tell if a red star is a giant or a regular star is that a giant star is actually going to have more carbon and helium in its spectra than you'd find in a regular star, just because it's already gone through fusion of almost all of its hydrogen or all of its hydrogen already. And so from the two filters, you get your effective temperature, and then you can find if it's a giant star or a supergiant, and with the radius, and you can calculate the luminosity. And then from that, it's another distance equation here, where now it factors in the absolute magnitude, and then you can solve for distance this way.
Lowercase m would be the
apparent, and then uppercase is the absolute.
All right, so I'll read it out if you're not seeing it. It's 100 to the power of m lowercase minus m uppercase divided by 5. That's this exponent divided by 5 equals f sub 10 over f. And what's that's the
flux at a distance of 10 parsecs versus the flux at what we see, which is equal to the distance over 10 parsecs, all of that squared.
Okay.
And then an easier way, the standard way of writing it is where you kind of do lowercase m minus uppercase m is equal to 5 log 10 of distance minus 5. That's kind of the standard way that you write it, which is called the distance modulus.
Okay.
So next is something called standard candles, which are a whole lot easier to do originally. Because if you only have like the apparent magnitude when you're first looking at a star, it's all of those steps that you have to take.
Yeah, so it's about how apparent magnitude is about how bright.
Mm-hmm. And absolute is just at a distance of 10 parsecs.
Yeah, okay.
But then we have standard candles, which this really helps for getting the distance to galaxies, as well as they can just be used for like clusters of stars or just the star itself. So the ones that are used, there's I'll go through each of them. There's type 1a supernova, there's Cepheid variables, RR Lyrae variables, and then there's Hubble's law. So, and I remember on one of the shows that you had said like Cepheid or something. I'm like, oh no, no.
Yeah, sorry. Yeah, and I've heard it before, and when I said it, I'm like, oh no, I said it wrong.
Yeah, Cepheid, because it's Cepheus is the constellation.
Oh, okay.
Mm-hmm. And same with Lyrae is the constellation Lyra.
Okay.
So for type 1a supernova, this is a certain type of supernova that happens when white dwarf stars merge. So stars that have, which is essentially like the remnants of a star that never went supernova to begin with. When they merge, and if they reach a certain mass, then they'll go supernova, and if they will have the exact same light curve, no matter which one it is. It has to reach a mass of 1.44 times the mass of the sun. That's what this symbol here is.
Ah, I see. So M sub
O dot.
Do you say O dot?
It's you just say solar masses is what you'd say.
Okay.
That's just the symbol for the sun.
It's just a little circle with a dot.
I like that symbol.
Yeah, it's just you'll
Circle
see
dot.
symbols like that. Yeah, circle dot. If you really want to say it that way. But yeah, the 1.44 solar masses is known as the Chandrasekhar limit because there was a guy Chandrasekhar who discovered this. And
so the point is that if there's two stars that were not massive enough, when they crash into each other, then their mass gets large enough, and that's the critical amount. Is our sun is just arbitrary. It happens to be the one we have close.
Yes.
So we base a lot of things off of it, but okay.
Yeah, so when these two stars, they both would have to be white dwarfs because it gets a little more complicated into that. But if the two stars are white dwarfs and they merge, they'll have, and they reach this mass, they will all have the same light curve. And since they have the same light curve, we've found that we found what the apparent magnitude is for that light curve for the peak of it. And so when we can get the apparent magnitude of it just from observations, then we can just use that distance modulus equation to calculate the distance. And so that works really well for very distant objects. So that's one of the standard candles.
Okay.
So Cepheid variables are a type of star that, oh my God, my cat, stop. Sorry.
His cat's getting hungry.
Yes, my cat is getting hungry 2 hours before I feed her. So Cepheid variables are named after Delta Cephei, which is the first one that was found in this category. They follow what's called a period luminosity relation. And so that relation, it is found that, hang on a second. Oh, sorry. So for Cepheids, it's that they all have like different masses and everything, but their luminosity and their period follow a trend line. And from that trend line, we can get like this graph that I have showing here. It is the logarithm of the time versus the absolute magnitude. And so if we can get
the logarithm of the time. So this is Cepheid stars have a varying brightness. And so what you're looking at is the difference between the peak brightness and the brightest and the least bright.
Yes. Yeah.
Points of their brightness curve.
Yeah. Okay. And so they have a different period relation. So if you can get the period of the star, then you can get the absolute magnitude of it. And since you get the apparent magnitude from looking at it, you once again can get the distance that way.
What's a normal amount of time for this variation? Is it seconds or days or years?
It doesn't have it on here. I forget exactly, but it has here. It's the units of days. So it's usually around like a day and a half, 2 days.
Okay.
Yeah, these are all screenshots from my my book. So thanks, Bob.
Okay.
So, and actually, one interesting thing is our pole star Polaris is a Cepheid variable. That is something I actually did not realize until I was rereading through my textbook.
Yes, and there's actually 3. Is it correct? 3 stars actually.
It's, I believe 2.
Or 2.
I think it's 2. It might be 3.
Maybe Sirius has 3, as I'm remembering.
Sirius has 2.
Okay.
Yeah, and that one's actually interesting because that second one is a white dwarf star.
Okay.
So then there's the next type of standard candle. It's another type of variable star, the RR Lyrae variables. So there's a spot in when a star is going through its end stage, it's called the instability strip, which is when the stars are variable stars. So when they have differences in their brightness. And I have here on one of the graphs, there's a really small little spot where you have your RR Lyrae variables. And also on a second graph, I have this where it shows the track that the star goes through its lifespan when it's a variable star. It's a very complicated looking graph. So,
it is, yeah. So near the end of the star's life cycle, they vary, like their how bright they are and their different behaviors.
Yeah, and that's because it's gone through its fusion for hydrogen, and now it's fusing different elements. And
it starts to tick up the atomic mass scale.
Yeah, and then
fusing different elements along the way and consuming them.
Yeah, and then Then the other fun thing of they lose mass as well as they shed off material, which makes it even harder to be able to tell.
Oh, I see. Yeah, so it'll have some sort of a like the gravity starts to win, and it kind of bounces in and winds up kicking off some stuff.
And the reason, why it's a variable star is like it'll push material out and then it'll not have enough, and gravity will pull it back in and then push it out and pull it back in, and it'll do that.
And does this? Do you know the time frame for these? Is it years, days?
It's years.
Seconds?
I mean, for RR Lyrae stars.
These variation bounces.
It is again, I believe.
For those listening along, both scales is logarithmic.
Yeah,
so you have to like.
Actually, this one doesn't have. This one doesn't have. Sorry, I'm gonna have to look that one.
It's okay. It's okay.
Yeah,
but it's interesting to think that they start. There's no more hydrogen, so they move on up to different elements, focusing kind of more on the lighter ones. It's not like focusing. It's not like the star is thinking about what it's going to eat next. It's just physics.
Yeah, and actually, RR Lyrae, it's on the period of hours. So, normal one. This is just from online. It says is about 13.6 hours.
Okay.
So, and the other thing for RR Lyrae is that their mass window is a whole lot closer than the mass of Cepheid variables, because the mass of Cepheids go from about 4 solar masses all the way up to like 20 solar masses.
Okay.
While RR Lyraes are only about 2.5 to 3, so that makes it a smaller window. And so,
and with there's enough quantity of stars out there that there's enough in that range that are happening every once in a while.
Mm-hmm. Yeah,
going through this. Okay.
Yeah, with the millions and billions of stars, you're bound to find some of them. Which let's see, and then the next one is Hubble's law, which is the easiest looking equation ever. It's just the recessional velocity. So the
V.
V is equal to the Hubble constant times the distance that it is away. So the recessional velocity is the expansion of the universe, and it's how fast it's expanding from us to that position. So it's kind of like how at the edge near the cosmic microwave background, stuff is moving really fast away from us, like 99% the speed of light and stuff like that. But then stuff like the Andromeda galaxy is the recessional velocity is still fast, but nowhere near as fast. So with that, Hubble's constant, he originally measured it to be, the units for this is again a weird looking thing. He measured it to be 100 kilometers per second per megaparsec. So a megaparsec would be mega. That's how much is mega again? That is
kilo is 1,000, mega is 1,000,000.
Yeah, million. So 1 million parsecs. So the Hubble telescope was originally, its main thing was to measure the Hubble constant, and it measured 73 for its value. And I just have on my screen the latest value, because it seems like the value has changed at different times, because it's just people have measured it differently. That's the fun of astrophysics right there. And because I forget the two theories exactly, but there are two things in astrophysics where they need the Hubble constant to be a certain value, and it's right in between what they need it to be.
Oh, so they can argue about who gets it.
So, and that's why I don't want to do theoretical astrophysics. I like my observational.
Oh yeah. So for reference, so 100 kilometers per second per megaparsec. So now you've got time and parsecs in there. So could you clarify then, how long should it take to do the Kessel run? Can you do that in 20 parsecs, which is not a unit of time?
Brilliant.
Yeah. I find it funny because I wonder how many people know what a parsec is and know that's a distance.
It's yes. And for reference, that's from Star Wars, where, and certainly George Lucas had probably, who wrote it, didn't really know what he's talking about when he said that, when he had said, Han Solo said that he did the Kessel run in 20 parsecs, as if it's a unit of time when it's a unit of distance. And 20 parsecs is what, more than 60 light years.
60, yeah, over 60 light years, 64 light years, something like that.
Yeah. So, but they did try to fix that in the movie Solo.
Oh,
which
I never watched that one.
I wasn't satisfied with their fix of it, by the way.
Yeah. And then also a lot of people think light year is a measurement of time.
Yeah, it's distance.
Yeah. So, yeah, it's.
All right. So Hubble's original measurement was 100 of those units, and the current measurement is about 73.
Yes.
So does that mean that it's changed, or does that mean that the precision of measurement has improved?
Precision of measurement. It's also better to have a space telescope than a ground-based telescope.
That's true.
So now it always helps.
Yeah.
This is meant to. The idea is that it is the universe expanding at a certain rate.
Mm-hmm.
So is the universe expanding at a varying rate? Is certainly a question people might wonder about.
Yeah, that one is a little hard to understand, actually, because for me, myself, I always question that too, it's because of the different measurements of Hubble's constant over the years. I'm like, well, it depends, I guess, on what parts of the universe they're looking at exactly, because I don't know if they're looking the full thing, because it's like, are they just giving an average? I'm not sure.
Yeah, well, and that goes into differing ideas about what the universe does. Does it expand and contract? Does it expand indefinitely? Is it a constant expansion? Is it an accelerating expansion?
Yeah,
these things are not. There's agreement on at some levels, but certainly there isn't like, yeah, this is definitely what we think it is.
Yeah, this is when you get to the points of astronomers starting to disagree, but at least having a general idea of everything. But yeah, that stuff's really difficult. That is something I haven't had a class on myself.
That's the edges of this particular field of science, and every field of science has an edge, a leading edge of things that. The answer to many questions is we don't know yet.
Yeah, that's a lot of that, especially when you get to the edge of the universe, which is the cosmic microwave background and everything. Yeah. Which is, again, in itself crazy.
These photons that started back then and they're getting to us now because the fabric of the universe expanded is that concept is difficult.
That concept, space-time, a lot of stuff in quantum and relativity is really hard to wrap your head around. So
that's for sure. Okay. So yeah, I see now we're down to these two equations on Hubble's law.
Mm-hmm.
Z equals gamma observed when it minus gamma emitted over gamma emitted. What is this?
So the gamma observed, or the lambda observed minus
lambda, sorry.
Yeah. Lambda observed minus lambda emitted. That's that's pretty much the redshift.
Okay.
So like when you have for the speed of sound stuff, it's when an ambulance drives by, or one of my physics professors is an F1 fan, so he uses an F1 car driving by.
Okay.
And so Z is that redshift divided by what the actual emitted wavelength is. Lambda is the wavelength of light. Yep. And then so you'd get the distance is equal to C, which is the speed of light, times Z, which is the speed of the, is the redshift, divided by the Hubble constant.
Okay. And that's the distance to the star then?
Yeah, distance to the star, galaxy, whatever.
So, all right. So you went over what? There's 4 different, is this the end of your
yeah, it's
PowerPoint?
It's kind of fast that I...
So yeah, all right. So there's 4 different ways using standard candles.
Mm-hmm.
And the previous one was, I forgot what it was, luminosity?
All those...
What do you...
are Lyrae stars or... Hubble?
No. But before the standard candles.
Yeah. Magnitude, flux, luminosity, and temperature.
Okay, so that's 5, and then
and then parallax.
Parallax. So there's 6 different ways. Maybe there's others, but these are like the kind of major ways to get distances to stars. And of course, it depends on the type of star. Some stars don't behave in a way that you can use all of these different things.
Yeah.
But we can use then multiple on an individual star,
mm-hmm.
right?
Yeah, and then actually one thing I left out, which makes it even harder for measuring distance, is what's called interstellar reddening as well. So dust in between you and the star. So that's especially a problem with star clusters, which is something I'm researching. And the star cluster I have is something called differential reddening. So it's different at different points in the star cluster.
Okay.
So the distance measurements, like every paper I've looked into has a different measurement for it. So it's like, which one should I use?
Yeah. So it's like you get your base case, and then, so then we get our complications to it that reduce the precision if we don't take it into account.
Yeah.
Right. So, all right. So we've got, for an example, Polaris, there mm-hmm. is parallax.
Yes.
It's pretty small, but there's parallax. And then it's a Cepheid or Cepheid.
Yes.
So you can use that as well.
Mm-hmm.
And you said it, and I still got it wrong even after you said it. Are there other measurement techniques that we can use for Polaris? I'm picking on Polaris because it's one of the.
Those are really the main ones, because like for Hubble's law, it's really too close to have a huge metric for that. Because Hubble's law you really just use for like galaxies usually.
Okay, which are much farther away.
Yeah, like Andromeda. The Andromeda galaxy is like 200 million light years away. So,
is that the nearest?
Yeah, that's the nearest major one. There's smaller ones, the large and small Magellanic Clouds in the southern, which can be seen in the southern hemisphere, which are closer, but which is a different topic in itself.
Yeah. Okay. So somebody was mentioning that recently, and I don't know how recent, I think in the 90s, that the distance to Polaris was adjused by or improved in its accuracy or precision by 100 light years.
I'm not.
And I actually looked it up, and over time, it's like 320 to 420 or something like that light years away was the variation in kind of recent times.
Yeah, that's a pretty big change.
It is, but it's still as a percentage, it's not insignificant.
Yeah, it's just that's some history, I guess, that I just didn't really know actually.
Yeah.
Uh,
So you're focusing more on distant, like, galaxies.
yeah. Well,
In
right
your
now I'm focused
style.
on certain type of star. White dwarf star is what I'm focused on at the moment. But actually, for my PhD, I think I'm going to be moving into galaxy stuff.
I see. Okay. All right. Do you want to, if you're done sharing your screen, you can.
Oh, yeah.
Yeah, you can stop whenever you want. All right. Well, Mr. Industrial Nerd.
This blows my mind. Okay, so how Hubble's constant? So Hubble's constant changes?
Well, it's not that it changes, it's just that the measurements change just because.
Yeah. I mean, it's seeing constant, but then wait, no, it's this. Yeah, that just kind of I don't know, it screws with my head a little bit. When I think of constant, I think okay, a constant, exactly. and it's a variable. Yeah, that just gets.
Is it that it's a difficult thing to measure?
Mm-hmm. It is very difficult to measure because it's just there's a lot of factors involved, and honestly, I can't believe that Hubble himself was able to do it with a ground-based telescope.
Yeah. And of course the leading edge of whether or not maybe it is varying, or if it's different in different directions or something. I don't know.
Yeah, that's one thing that I'm even like not sure on, and because I mean, yeah, just looked it up just to make sure. I mean, there's been values that have suggested 69.8. There's 74, 73.
So there's a range. The constant is a range.
Yeah, I think there's. Nice. I think one of the theories for that I was mentioning earlier. I think it needs like 75. So
75 works nice. For them.
Yeah.
So it is challenging to be measuring things that are very distant, and we can't go there. We can't bring out a tape measure. We can't intentionally ask a star to go supernova so that we can do things on them. We just have to wait.
Yeah, we want one to go supernova.
Yeah, and hopefully we have things looking at it when it goes supernova. And so actually, are there ways, probably when it starts to vary, where we're like, well, this one's very likely to go supernova soon, so let's really focus on it?
Well, I mean, with it's going to go supernova very soon, that can mean in the range of like hundreds of thousands of years. Astronomers.
I hate it when that happens.
Which actually for us, the closest star to us that could go supernova is Betelgeuse, which is probably in the range of 100,000 years to go supernova.
Oh, plenty of time.
Yeah.
Now, for reference, that is the second time you've said that word.
Yeah.
Be careful. Third time, and he shows up.
I was like, wait a minute. Right. Oh, yeah.
It took me a while to get that one too. That's good. Now, flux. What exactly is flux a measurement of? I mean, luminosity. I know what luminosity. The brightness of an object. What exactly is flux?
Flux is really like the energy received, like at a certain distance. I guess you could say.
Okay.
Which is like the inverse square law. So
yeah, okay, I gotcha. The energy that makes sense. Yeah, so I'm a big solder person, so when I hear flux, I think of pine resin, and I'm like, oh, wait, hold on, there's a Astra. No, wait,
yeah, no, different definition.
Thanks for clearing that up.
Yeah,
are you soldering pipes or electronics?
Electronics, the good stuff, the good stuff. Yeah, with the 6337 solder, and
I don't really think of soldering anything other than electronics myself.
I was soldering some plumbing this weekend, so
that does not sound fun.
Yeah,
a new faucet in the bathtub. All right. So have you all right, so you said you work with Hubble. Like you've done like specific things with the data from Hubble. Have you have in any of your projects been like, okay, we are going to put in a request to have Hubble point at this thing for a certain amount of time? And
so the data I'm using originally is actually old data that just never really got published, but it was from a colleague of my advisor. And then we requested time for Hubble itself, but it got rejected, which sucks. But the funny thing is, though, with the Hubble telescope, even though James Webb is up now, the amount of time requested versus the amount of time there is to use is 7-1.
At Hubble?
Yeah, for Hubble alone.
Wow. I'm sure James Webb is
even more.
Gets a bit more demand. Yeah, so the demand for Hubble, do you know, did it go down much because of James Webb? Did it shift, or is it like the same? It doesn't matter. The interest is still huge.
I mean, it probably went down a little bit, but still, Hubble's working. It's a great telescope. And because of that, I saw NASA extended the Hubble mission. So
yeah, with that, as long as it's still working.
Mm-hmm.
That's great. I heard that. So there's the other one that's similar to it that goes in an airplane. Sophia. It doesn't ring a bell. All right. Well, apparently I don't know much about it, but apparently there's another.
Is that a newer one? No.
It's about as old as Hubble, but it's essentially the same type of telescope, but it's in a 747 or something like that, and it flies.
Yeah, I have heard about that one. Okay. I don't think that one's in use much or anything.
If I remember right, they kind of they're done with it now. But
now, which one had the blue screen of death? The Windows blue screen of death, was that Hubble?
Hubble did have problems at first, where when it was first sent up, the mirror that's used for reflecting the light was actually misshaped. So So luckily the space shuttle program existed still then, so they could go up and fix that.
I don't imagine when they built the Hubble that the mirror was a end user serviceable part.
Yeah. The company, I forget what company made the mirror, but they got in big trouble.
Yeah. Like, oops. We'll send out a guy. He'll replace it.
I know, right?
Under warranty.
He'll be there in 2 parsecs.
That's what the payload specialist is, right?
Yeah,
that's great.
That's interesting. So you've requested Hubble. They said no. So you're just looking at some data that somebody successfully got time from Hubble in the past, but then just parked the data.
Yeah, they've just never got it published, and they've retired since then. So
okay.
It was actually funny when I was looking through papers to find for like my introduction and everything. I found a paper that was like, this is interesting. This is a lot of the stuff that I'm looking at. And I showed this to my advisor. He's like, yeah, if the data you had was published, it was going to be in that paper.
Oh. So they were going to do it. In the end, they didn't. It was they published the paper of doing whatever they did, but just not this particular data. That's interesting. That's cool that you can get and use the old data. So I wonder, with the amount of time that Hubble has been doing stuff, there probably is plenty of data out there.
Yeah, and actually anyone can get the old data. There's the website Hubble Legacy Archive, which has like all the raw images, all the unedited, unstitched together stuff, which is what I'm using.
Yeah, because NASA's deal is that there's everything they do is supposed to be public domain.
Yeah. So the Hubble Legacy Archive goes up to 2017, I think.
Okay, so there's a delay in getting it.
Yeah, because I mean everyone's still doing research with their stuff. So,
so there's like a window of time where they kind of give them a little buffer to say, all right, well, you can. Is that what it is? You have time before we release this publicly for you to do your research and publish it?
I mean, I assume, or maybe it's just once the stuff is published, then the data is able to go out, or when they're just like, all right, whatever, I'm not doing this, data's out, or
okay.
I'm not sure exactly. I just know that's where I got my data.
Okay. The politics of it is beyond you.
Yeah. My advisor was just like, here's this, go do it.
All right. And you said your schooling is done. You're gonna graduate soon here with your master's?
Yeah, I'll be getting my master's in the summer, and then immediately after that be starting my PhD.
Wow. All right. And so what do you do when you have a PhD in this field?
Well, I'm hoping honestly to stay like in academia sort of stuff, because I love doing research. But with that, it's very hard to get jobs in academia. So probably it'll end up being like working in the private sector, or even like maybe working for NASA, but NASA's more engineering. Same with SpaceX. But with a physics degree as well, I mean, you can do engineering with a physics degree, because I mean it's kind of physics is the general stuff for engineering.
Yeah. So that means if you're in academia, you're probably teaching as well as research.
Yeah.
Right.
But it's the guy that I interviewed with actually for my PhD, when he asked like, what do you want to do after this? And I told him I want to stay in academia. He's like, that's just before you get too far into that, just know it's a very small percentage of people that actually stay in it.
Ah. All right. So hedge your bets.
Yeah.
Plan on, you can hope for the plan A and plan for B or C or D. Yeah. So what kind of, I don't know, what kind of position might in the private sector be more specifically applicable to what you're studying?
I mean, for that, like some of the stuff, I mean, there's telescope operator jobs, which I mean, I don't know if that's more PhD level, but that's something that I've seen and found interesting itself, because that's where it's like at the actual observatories where it's like they need something pointed, then you go and do that, because everything's done computer stuff, so you don't have to travel everywhere.
Yeah, so somebody will request time, and somebody has to be on site there to be doing the work.
For some of the telescopes, yes, but then other times it's just for the astronomers doing observational, you have to stay up all night and still doing all your stuff.
Telescope operator. That sounds like a fun, interesting. Oh, so what do you do for a living? I'm a telescope operator. Oh,
yeah. But whenever I say to people I'm doing physics or astronomy, they're like, "Oh," they like, eyes wide open. But,
nice. Yeah, I suppose it's not a 9-to-5 job to run the telescope.
That's more
at night.
It's like a lighthouse almost, you know.
It'll be 9 p.m. to 5 a.m. job. But yeah, stuff with astronomy. I mean, just staying up all night is not fun, but it is fun to actually use a telescope. And the staying up all night is one reason why I hate daylight savings time.
Oh yeah,
because it makes you have to stay up an extra hour.
Completely.
Oh totally yeah, I prefer it how it is now, where we just had daylight savings shift here in the spring. I definitely prefer it this way. I would keep it this way all the time if I could.
I saw a thing actually that was saying why you should not have it that way in the wintertime, though. Where
I disagree already.
Where it's sunrise in some parts of the Midwest wouldn't be until 10 p.m. or not 10 p.m., 10 a.m. There would not be sunrise until 10 a.m.
Oh, that's good. Then it wouldn't bother me while I'm sleeping in.
Like, imagine if Canada did that, where they just did daylight savings time permanent and they didn't have sunrise until like 10 a.m. Gosh.
I was in Anchorage in July a couple of years ago, and they're at 60 degrees north. I'm in Minnesota at 45 degrees north. They're at 60 degrees north. And it was midnight, and it was bright. People just walking around like this was nothing. It wasn't bedtime yet because it was still bright.
That'd drive me crazy. I wouldn't know what to do. Like, oh, it's bedtime. Oh, look, the sun's out. Let's go for a walk. Wait, hold on. It's bedtime.
But it's the opposite then in the winter, where it's like you have just this short window of time where it's bright and it's just dark. So much dark.
I couldn't do that.
Yeah, I know that there's some town it's always like, for the news, it's always some minor news piece where it's like some town in northern Alaska is in the Arctic Circle. So it's like there's months where they won't see the sun.
Yeah.
Depressing. Totally depressing. Yeah. I couldn't do that.
Yeah, no kidding. For why? You can and it's not just cold, it's really cold.
Yeah, it's
really cold. I don't know. Some people like it. Go ahead and like it, people.
Cold and dark. I don't know. I call them psychopaths, but okay.
I like cold, but I don't like it dark that long.
Yeah. All right. So what, do you have like a personal telescope of your own?
No, I don't. I wish I did, but in the past I did, and then I just never used it.
Okay.
But I wish I did. They're just kind of expensive. So
They are.
because I mean a decent one, like one that I would want to get, would be like 6-inch diameter, which is decent size. It's like $300 at minimum, like on sale $300.
Yeah, and for an indefinitely long college student,
yeah,
that's a lot of money.
yeah,
Completely.
I have one friend that's even more indefinitely long because he's doing a postdoc right now.
Oh, there you go. So anybody interested in sponsoring Eric with a telescope, you could get your name plastered on the side of it, and he'll thank you every time he pulls it out. I'll hook you up.
Yeah, as a grad student, I definitely don't have the money for it myself.
Yeah.
I need
That's
that
great.
secret NASA money, but I don't get that yet.
NASA, yeah, they're a little tight on that purse there. So, but you get data from Hubble, and have you done other things with other telescopes in your studies here?
In my master's degree, I have not, but in my undergrad, I actually did get to use other telescopes, which was staying up late for those.
Okay, so you actually got time on them.
Yes.
Which ones?
There was one. I mean, there's smaller ones just that my school owned. There's one that we use that's in Arizona, and there's one in Chile that I got to use.
Oh, nice.
And which what are the specs of those?
They're both meter diameter, which is pretty good, but not the biggest telescopes. But you can see really far with those. So
yeah, and they're reflectors.
Yeah, pretty much every telescope's a reflector because they're cheaper and
if they're that big.
And they don't have like much refraction from the like they don't have lenses causing refraction. So
or chromatic aberration.
Yeah.
So
Big
chromatic
words.
aberration is where
aberration.
Different frequencies of light refract differently through lenses, and if you have a strong amount of magnification, that can be enough to cause some issues where you have like purple light refracting a certain amount one direction and red light refracting a different amount, and they get fringes to the sides, so we have to do things to correct for them. But if you have a reflector, which is a curved surface mirror, then that doesn't happen. It just bounces right off. Plus, you don't have a gigantic lens.
Yeah.
Imagine a 6 meter diameter glass lens. It'd be heavy.
Yeah,
burning ants.
Instead you have 6 meter diameter mirror, which is still
it's a lot, but it's a lot lighter. And but imagine the ant that you could burn with that 6 meter diameter.
But there's one funny story though from one of the telescopes I got to use was before I got to my college. One of my professors had time on this telescope, and there's always like safety stuff to keep it so the telescope doesn't go like past 90 degrees. So if you're looking at something on the horizon, and it failed. So it went upside down.
Oh no!
The mirror somehow did not fall out of the telescope.
Wow. Oh, we can see the floor. Oh, wow. Look, we can.
But for the group of colleges that like co-own the telescope, he became known for that.
That's such a mirror flipper. Those mirror flippers.
Because I had met some people from other schools, like some of the professors from the other schools, and I was like, "Oh, this was my professor," and he was like, "Did he tell you the story about how he turned the telescope upside down?"
That's great. That's great. Epic.
All right, so if you go to your doctorate and you want to look at these things farther away, galaxies and stuff, then even Hubble might be not enough. You might have to go for the big dog.
Yeah, Hubble can see really far. But James Webb, actually, the guy that I've been talking to who is going to be my advisor, he's actually already had time on James Webb. So it's like I might actually get to use it.
He's an astronomy legend, a celebrity in the astronomy field, huh?
Sure.
If he's been, he's
I've been on the James Webb.
I know it's quite a flex you can use.
There you go. That's yeah, that would be interesting is there must be some sort of hierarchy in the astronomy world of different people that have different amounts of.
I mean, it's really just does your research look good to the people accepting proposals? Yes or no?
Yeah.
And I guess for us with Hubble, it was no. But
yeah, with a 7-to-1 ratio of requested time to time that exists.
Yeah.
They need to fire up the TARDIS around there so you get a little more time.
Yeah.
I wonder, you probably don't know what the requested time to granted time for James Webb must be bigger.
Oh, it's definitely going to be bigger. I don't know the number, but I would guess it's double digits for that one.
Yeah, that'd be crazy. Yeah,
because I'm pretty sure people were making proposals for it before it even launched. So
yeah.
So it's like, imagine if it had failed, and then it's like all their proposals, all their research projects would have gone down the drain.
I watched that launch and I'm like, just imagine the pressure. It's got to be perfect.
Yeah.
It's not like, oh, well, Starlink, SpaceX is setting up another 60 Starlinks. If they all explode, it sucks, but it's not that big of a deal. They can make more.
Yeah. And then also, if something goes wrong with the James Webb Telescope, we can't send anybody out there to get it because it's not orbiting the Earth.
Mm-hmm.
So.
Yeah, that the warranty repair guy is going to have an issue.
It's orbiting a Lagrange point, so we can't get to that with it just.
All right, now you've said Lagrange point. People got to know what's Lagrange point.
So Lagrange point is a point where the gravity of the Earth and the Sun kind of match each other. So the point where there's 4 different Lagrange points for every planet, or really any object that's orbiting the Sun. 5. Oh, 5. Yeah, 5. Sorry.
Go through the 4. All right, all right. So
yeah, so the one I'll just say the one that it's at, which is the most stable of them, is the L2 point, and that is the point that is the point where it's in Earth's shadow. So the
gravitational shadow.
Yeah. So it's orbiting this point, and so for that, it's further out from the Earth, so don't have to worry about any disturbance from what can be called Earth shine, which would be even light pollution for space telescopes.
And it points away from the Earth. There's a big shield.
Yeah.
And that shield is between the Sun and the Earth. Yeah, the Sun and the Earth are essentially in line with each other from the where James Webb is.
Mm-hmm.
It's 5 layers of shielding. So that's L2. L1 is halfway, or not halfway, is partway between the Earth and the Sun, about 1 million miles. That's where Epic Discover satellite is, and that's looking at the Earth.
Yeah.
And
L3
then
L3 is on the opposite side completely, and then
so it's essentially Earth orbit 1 AU away from the Sun, opposite the Earth.
Yeah. So there's L1 and L2 are close-ish to the Earth. Then L4 and L5 are I'm not sure exactly what fraction away from.
It's about a third, I think.
Yeah, it looks.
So it precedes our orbit and follows our orbit by about a third of the.
Yeah.
Is it a third? No, a sixth. A sixth would be about, if you look at the number. Anyway, look it up.
I just pulled up a diagram just to see, and it's about a sixth for each of them.
And I've seen people ask, like on Quora, could you send something to sit partway between the Earth and the Moon? And of course, the Earth Moon has Lagrange points as well.
Mm-hmm. So
yes, you could have something in a somewhat stable position between the Earth and the Moon. Now, they're not necessarily stable. Like L2, you actually orbit the point, and it takes a little bit of work to stay in orbit. It's like at the top of a hill.
Mm-hmm.
And if you don't do a little bit of work, it can kind of wobble off. But L4 and 5 are like at the bottom of a valley. So I've seen people think that maybe there's like just some garbage that's collected at 4 and 5 garbage, like little bits of matter.
I mean, that's very noticeable with Jupiter, actually, because you can actually see all the asteroids that have been captured by those points, and they follow around with Jupiter, which is kind of interesting.
Oh, I didn't even think about that. Yeah. So, but the thing I saw about Earth is that there could be things in 4 or 5, but it's hard to look at.
Yeah.
So
Lagrange in French means barn in English.
Really?
Yes, I just Googled it.
It's actually a guy's name.
Yeah, it's a guy's name. So it's
was he French?
Yes, he was French.
Okay, all right. It all makes sense now.
All right. Well, Eric, thank you very much for explaining this. And thank you to Industrial Nerd for joining. If you are interested in, Eric, would you mind your contact information? I could have asked you beforehand, but no, I'm doing it right now.
I mean, I guess.
How about this? On the YouTube, on the Toon Show, find this video on YouTube. If you want to ask Eric a question in the comments, go.
Yeah, and then I'm just Eric Burns on YouTube. So
there you go. You'll
might see me in the comments of Toonsday stuff as well.
Yeah. So I have my MC Toon live channel where I debate live, and my Conspiracy Tunes channel where I just have pre-recorded videos where I end up laughing at the flat earthers an awful lot.
Yeah.
And
I'm hoping I said stuff correct. Otherwise, Phil Bell might get mad at me.
Oh my goodness. There are some incredibly smart people that watch these. I'm like, what are you guys doing watching me? You guys are way smarter. Anyway, there's a lot of smart people that watch these, and I'm always quite amazed at them. So anyway, if you want to see this video, do go to the Toon Show on YouTube. If you like what I do and you want to support it, you can find me on patreon.com/mctoon. And with that, thank you very much. We'll see you next time.